I'm about to start streaming.
Huh? Yeah. No, do it when you're absolute. Wait, who's going? Are you going first?
Yeah.
Okay.
Okay. Wait. So how do I publish this? How do I make it
No,
discovered?
it's already done. It's already done.
Okay.
Okay.
So. Thanks.
This is mine. So how do you use the crack?
I feel like I'm gonna die.
Oh yeah. Can you ask them to
Check it.
yeah. Can you like
I feel like I'm
wait.
gonna die.
Oh yeah. Can you ask them to
Check it.
yeah. Can you like wait. Oh yeah. Ask them to
On the story. Check it.
yeah. Can you like wait. Oh yeah.
Yo, you're not gonna be able to see who somewhere.
Wait.
Yo, you're not gonna be able to see who somewhere. Yo, you're not gonna be able to see who somewhere. Yo, you're not gonna be able to see who somewhere.
expected.
Great. Yeah. Hi, both of you.
Speak into the microphone.
Wow, I think I agree
Great.
with this. So thank you for coming.
Hi, both of you.
So first of all, it's a super revision day next Tuesday. We're going to go through thank you for coming. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you for coming. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you for coming. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision day, you guys know about next Tuesday. No, we're going to go through thank you. Since you two are only revision.
Like, I was, yeah, I'm like really confused.
That sounds like there's two microphones. Wait, is the other one capturing it as well?
Oh wait, maybe that's why. Is it better now? Like, just give it like.
Yeah. Should only be like one of you. Yeah.
It's good. Alright, great.
Okay.
Okay, great. Okay, let's. Oh, hello. Yeah, please fill in the attendance form. So we get money. There's also a super revision day next Tuesday where we'll go over exam bank questions with pass. So yeah, easy marks. Yeah.
Yes.
What time does that start?
10.
I'd say it's 10 a.m. to 4 p.m.
Yeah.
Obviously, you can come in whenever.
Yeah.
In and out. Yeah. Thank you.
Pass. 10. Wait, no. What color is this? 10 to 4. Pack it up, bro. Okay. Everyone good? Okay, let's get started. So today we go over the 5 calculus chapters. So we'll start with functions of several variables, then go into a bit of integration and oh my god, my bad. And then go into ODEs, Taylor series, and then application of integration. Could you do the attendance form real quick, please? Can you do the attendance form real quick? Thanks.
Anyone that comes in, I'll just show it to them individually.
Yeah.
You don't need to worry about it.
Okay, great. Okay, so let's start off with partial differentiation. So partial differentiation is it is basically, it's very close to what we normally know as differentiation, but we only differentiate with respect to the variable down here, and we use the symbol. And we treat every single other variable, for example here y, if we take the partial derivative with respect to x as a constant, so we just take it to the front, similar to like, for example, a 2 or whatever. Yeah, so if we look at this example right here, if we take the partial derivative with respect to x, for this one, simple, it's 3x squared. But for this one, we'll just take it as y instead the y would be a constant instead of actual variable. So, and x, well, if we differentiate that will just be 1. So that just goes down to y. And this, since y cubed will now be a constant, it would take respect to x. So this would just go to 0. And if it's going to take with respect to y, it would just be quite similar. So this would just go to 0. this, since we're taking respect to y, x will be a constant, and y would just go to 1, and this would just be 3y squared. Good? Okay, yeah. Obviously, also some notations that we can use. We can either use something like this, that means with respect to x, or something like this, that means also with respect to x. Good, okay, great. So here is a useful theorem that, for example, if it's easier to find the partial derivative of y first, then we can use that, but we can also swap them around. So whether we take the derivative with respect to y or with respect to x first, it doesn't really matter. So a good example is here. So for example, for example, right here, this example, it would be quite annoying to take the derivative with respect to y right here, right? Because we go to product rule, chain rule, and a whole bunch of annoying things that would probably not very helpful. So if we want to look at, so the function was x squared y squared plus e to the inverse tan y squared times cos cubed sine y. So, and they asked us to find x and then y. So if we just follow this order, we have to do y first, and then we do the x1 next. But that's probably not great, as I said earlier, it's a bit annoying. So let's swap them around. So this would just equal to the partial derivative with respect to well, x first and then y. So if we look at taking the partial derivative, right, so it'll be like this, right? Take partial derivative with respect to x first. So this entire thing would just be a constant, right? And that's just 0, right? And then this y squared would just be a constant, so we chuck it to the front. X squared, that goes to 2x. And well, let me tidy that up. So 2xy squared, that's much easier, right? So that's just 4xy. See, much simpler. Good. Okay, let's move on. Okay, so tangent planes. So tangent planes are essentially it's similar to tangent lines, but this time in 3D. So how we can do it is if we want to find a normal vector first. So normal vector, we can take the normal vector if it's in 3D. So because f has x, y, z, we'll take it to be the first component. Well, it's right here. The first component will be the function taken to the partial derivative with respect to x. The second one with respect to y, and the last one to z. And then we just sub in the point at P, and then we are done. And if they ask us to find the Cartesian equation, we just sub it into the point normal form of the line. Good? Good, okay. So here's a question. 2 minutes, 1 minute, have a look at it, and I'll start going over it. There should be some aircon now. Okay, great. So let's get started. So the first thing we do is, well, we get given this equation, but what we need to first define is we need to find a big function, well, big F, x, y, z. And essentially we want to chuck everything on this side, so there's a 0 on one of the sides. So, well, I like to keep the x, y positive, so let's go F equals to 3xy squared minus z. That will equal to 0. So part A asks us to find normal vector. So as I said earlier, the normal vector would just be three components. So the first component will be taken to the respect to x, y, and then z. So the first one, well, will be 3y squared. The second one will be 6xy, And the last one, well, this would be constant. That's gone, so that's -1. Good. And if we evaluate at P, so, and at P, that means we just sub in this into here, this into like here, and then that's just gone. So now we have 3 times 2 squared, 6 times 2 times 1, and -1. That goes to 12, 12, -1. And that's my normal vector. And if we look at part B, the Cartesian equation, so it would just be, we use the point normal form up here. So it will be n dot product of x minus p, p like that, equals 0. So if we substitute it all in, it will be 12, 12, -1. Well, this would just be x, y, z, because that's just any point in our surface plane. So it'd be x minus first component would be p will be 1, y minus 2, and z minus 12. Good. Equals 0. And if we just do a normal dot product, I'll skip the steps. So that should give us to a final answer of, well, actually, I'll just write it out. 12 times y minus 2 minus z minus 12 equals 0. And then that should all lead up to 12x plus 12y minus z equals 24. Good. Easy, simple, chill. All right, I assume that's a yes. Okay, great. Let's move on. Answer. All right. So the total differential approximation. So if we are given any function f, if we want to measure, if we measure the change in f, we can just take the partial derivative with respect to x, times it by how much is changed, and then do the same thing for y. So yeah. So if I look at, for example, area, the only thing that would, so area is equal to xy, right? So if I change area, the only thing that I can change to area, or to cause a change in area, is if I change x or if I change y, right? Like if I change what's the temperature, probably won't change, right? Good. Okay, great. Okay, so yeah, so if we want to measure the area, so we can just use the triangle inequality, and that will give us something like this. And yeah, good. Just formula bashing, unfortunately. All right, great. So here is an example. Wow, it's almost like I just predicted that it's gonna be area. Okay, I'll give you guys a minute, 30 seconds, have a look at it, and I'll just go over it. Okay, so if we have area equals to xy, so we want to find the percentage increase in A. So in other words, we want to find delta A. So, but we know delta A just equals to the partial, or roughly equal to the partial derivative of A with respect to x times delta x plus the partial derivative A with respect to y times delta y. So let's figure out each component by itself. So let's look at delta A over x. So not delta, partial derivative. Okay. So with respect to x, so that's just simply y. And same thing with respect to y, that would just be x. And for delta x, if we go up here, when x increases by 5%, right? So that means the change in x will be 5%. So that means 0.05x. And the change in y will be negative 0.06y, because it's decreased by 6%. So if we substitute it all in, so that would be roughly equal to y times 0.05x plus x times negative 0.06y, and it will be 0.05xy minus 0.06y. So that would give us a rough change of negative 0.01 xy, and since xy is just equals to a, okay, turn that to a. So the change in a would just be negative 1%. Negative 1%. Change. Negative 1%. Good. Okay. Let's keep that. Is that good? Is it good? Good. Okay. Let's keep going. Okay. So chain rule. Chain rule is quite similar to if we do it in one variable, but this time you just have to go in a tiny bit more. So you know how for normal ones, if it's only one variable, you just have to make sure you get to the end. This is similar. If we want to differentiate with respect to t, so for example, f is xy, but x and y can then be separated a bit more. You need to find a way to get to final t. So we need to add in. So first we take respect to x, and then we go further in. So because x is a function of t, you need to differentiate that as well. And then same thing for y, and then you add them both together. So you can actually draw a diagram, but I think with enough practice, you can probably skip this step. But in the end, you just want to follow all the arrows to get to t. So this is the first bit, so here, and this is the second bit. So if you're along a path, you multiply them together. But if you go in between paths, you add them together. Great. Yeah. So here's a bit more complicated one. So if I want to go to s, I gotta go here, and then here. If I want to go to a t, I have to go through here, and then here. Yeah, great. And then if it's like the same thing, yeah. But so if it's like even more complicated like this, once again you just follow the arrows. So if we want to get to u, so you see how this entire big chunk, so it would just be these ones added together. Or you can go through the other way, go through t as your final step. So like this. Good. But it's hard to tell this, but best way to go is with an example. So have a look at this, and then we'll go from there. My bad. All right, great. So if we want to look at the partial derivative with r, so right down here, so we need to go through z, we need to go through x first, and then go to y, or we can go through z to y and then to r. So it'll be, so the partial derivative of z over r will equal to the partial derivative of x with respect to, or z with respect to x, and then we differentiate x with respect to r. And then well actually partial, but yeah, partial. And then we add the same thing, but in terms of y this time. Great. So and then we last thing, well, we can probably sub in a bit earlier, but we'll see how that goes as we go. So if we look at partial derivative of z with respect to x, that would just be, so y, well, let's look at this one first. E to the power of xy plus 2xy. xy. And if we look at x with respect to r, well, this would just be a constant. Well, this would just go to 1, and that's constant. So just be cos theta plus, same thing for y. So that'll just be x e to the power xy plus x squared. Because now y is so x squared is now the constant, and y goes to 1. So and that goes to sine theta if we take it with respect to r. Can people at the back hear me, by the way? Good. Because I can use this if you want. It's a bit weird. All right, great. So then we can just substitute in our values. So r is 1, theta is pi over 4. So if let's look at that. So x when r equals to 1, theta equals pi over 4. That's equals to 1 cos pi on 4, and that's 1 over square root of 2. And same thing for y. That's equals to 1 times sine pi over 4, and that's 1 over square root of 2. So that means xy times together will be 1 over 2. So if we substitute this all back in, so that means 1 over root 2 e to the half plus 2 times a half, well, cos pi on 4, that would just be, so when r equals to 1, theta equals to pi on 4. So cos, well, that's 1 over root 2 plus, well, basically same thing, 1 over root 2 e to the power of half plus, well, 1 over root 2 squared times 1 over root 2. Here, sine pi on 4 is 1 over root 2. And if we multiply, or if we simplify first and then multiply everything out, simplify first, that's 1 times 1 over root 2 plus 1 over root 2 e to the half plus a half times 1 over root 2. And if we do some simple simplification, plus, so, and then if we keep going on and on, that should, I'll just quickly write it out. So that should give us, well, these two added together will be 2 over root 2, which is just root 2. Root 2 e to the half plus 3 over 2. So it'd be e to the half plus 3 over 2 root 2. And you can rationalize it by yourself. Is that good? Good? No questions? Okay. Easy. All right, great. Let's move on. Yeah, so answer, that's just the answers. Great, so that's really a TLDR of functions of several variables. Great. Okay, let's move on to integration techniques. Yeah, so the basic ones are, well, first let's look at trigonometric. So if we get something that looks in this form, there's several good cases that we can actually work with. So if n is odd, all you need to do is you have to let u to be sine x, because then you can eventually simplify down using this integral. But this is identity, not integral. So for example, if you have sine squared x cos 3 to the power of x, cos 3x dx, here's u equals to sine x, so that means du equals to cos x dx, and then you can just go into here, sine squared x cos squared x du, sine squared x, and here you can just turn this into a sine square, and then you can substitute in u, and then it'd just be a normal, hopefully quite easy integral for you to solve. I'll zoom out. Yeah, great. So, okay, yeah. So same thing for if m is odd, but this time we just swap everything around for u equals to cos x. But just don't forget to put a negative in front of the sine x, so you don't lose silly marks. But yeah, so this time we swap around the sine squared x and the cos squared x, and we just use this integral. Yeah, but the tricky bit is when m and n are both even. So now we have to use some identities based on cos 2x, and so these two are it, and then yeah, hopefully should remember these. Probably will come in handy, but I'm pretty sure it'll be on the formula sheet. So yeah, but I think these slides will be uploaded onto the MathSoc website after this, and you guys can re-watch this on the live YouTube stream, which has 1 concurrent viewer right now. Pretty good record. Okay, great. So let's have a look at this integral. So, well, cos will just be 0 in this case, right? And that means it's even. So if we look at this, which case do we use? Since m is now even and n is also even, we just use case 3. So that means we need to use the identity sine squared x equals to a half 1 minus cos 2x. So if we evaluate, so let's just put this into our equation. So that means half times 1 minus cos 2x squared, because 4 is sine squared x squared is sine to the power 4x dx. And if we just take the 1 over 4 out, expand it to 1 minus 2 cos 2x plus cos squared 2x dx all over 4. And then we can keep going on a simple. Actually, let me just times it back in, so I don't need to be that hustle. Yeah, and then we can once again apply the same this identity back into here again to get it simplified a bit more, because we can integrate like cos 2x quite easily, right? But cos squared x probably a bit harder. So if we apply it again, so cos squared x equals to half 1 plus cos 2x, actually 1 of quarter minus half cos 2x plus would be 1/8 this time. But be careful, because this is x, but we're using 2x. So this one will now be 4x instead, because it will be cos squared 2x equals to half 1 plus cos, running out of space, 2 times 2x. So there's a half 1 plus cos 4x. Great, okay. So, okay, where was I? So this would be 1/8, 1 plus cos 4x dx. And if we simplify a bit more, so this would just be 3/8 minus cos 2x over 2 plus cos 4x over 8 dx. And if we integrate that, hopefully that should be quite chill. 3/8 x minus sine 2x over 4 plus sine 4x over 32 plus c. That's how you do trig integrals. No. We have 3 viewers on YouTube. Okay, great. Let's move on. So here's the answer. You guys want like a one without my messy handwriting. Here it is. Okay. Yeah. So same thing. This is using cos squared. So, but this one is we now use some product to sums, or if you prefer the other way, sum to product. I prefer sum to product, but that's just me. Okay. So yeah, here are just some identities. Hopefully you have seen these in high school or in your own time practicing. I'm pretty sure these are also on your formula sheet, so don't stress too much. Are we on the formula sheet?
I know this isn't necessary.
Oh no. Yeah.
Would you guys get a formula sheet 1A?
I think so.
I don't know, but just use maple either way.
Wait, we get a table of integrals. This is in the course notes.
Oh, see, even better. All right, great. All right, so let's keep going. So let's try this integral. So since we have a sine and a cos, so clearly we'll use case 1. So that means this integral equals to half sine. So as we go back up here, it'll be first adding the 2 together and then adding the 2, well, what's inside here, minus each other. So that means it'll be sine 3x plus 2x plus sine 3x minus 2x dx. So if we just simplify it a tiny bit, it's 5x plus sine x dx. And if we integrate it, that would just be negative cos 5x over 10 minus cos x over 2 plus c. I hope that's true. But if you want, put down my messy handwriting. Here you go. So if we have trig integrals, if we don't have trig integrals, sometimes. Actually, no, we're not there yet. So here's some identities that we can actually use to solve trig integrals. So similar to how if we sometimes we substitute u equals to u equals to cos x, we might need to substitute u equals to tan x or sec x, or in the unfortunate case cosec x, but I usually don't do it. So yeah, so here's some integrals for tan and sec that hopefully might come in handy. Yeah, so if we look at this one, it doesn't say up there, but a good way we can check this is usually if you can separate out something in terms of sec x, tan x, because that just goes integrate to sec x, and if I'll get left with a sec have 3x. So because this is just the derivative of sec x, this just be a pretty good reverse chain rule. But in general, how I like to do it is if tan is odd, usually I look for a sec x tan x. If tan is even, because here, actually no, if tan is even, sometimes I substitute tan x, but it depends. So go try some integrals and figure out the pattern. Yeah, so if you look at this, so because this is a derivative of sec x, this should be a reverse chain rule, be a quarter sec to the power 4x dx. Or alternatively, you can let u equals to sec x. So you got du equals to sec x tan x dx. And then so if you substitute back in, you'll get u to the power 3 du. And that's, take you all back here. What's this dx? Plus c or dx. Great. Okay, let's push on. So, reduction formula. So what reduction formula is you get a recurring chain. So like that means I can represent, or I can find the value of the next integral if I change this n into an n plus 1, and it'll keep going on by just subbing into this formula here. And how you like to do it is if you see a coefficient in front of this, in front of the in, you need to use integration by parts. If you don't see anything, that means you can just technically say it's like in plus 1 equals like 1 over n plus in. That means you can just find the expression in terms of this. So that means you can move the in to the other side. So you find the integral in terms of this, and then you can just work out the integral, and it should give you this. So yeah, just remember this, quite a little trick. You don't always need to use integration by parts. Okay, great. Yeah, so for this one, since there's a coefficient from here, we need to use integration by parts. So what do we do? So we can just, since we see a lot of n separated out here, so that means we can try, let's go 1 over 1 plus x squared, or to the power of n, and the next one can just be 1. So times 1. So if we differentiate that, that should be 1 over negative 1 over n, 1 plus x squared, n plus 1, which kind of resembles what we need up here. And we do the chain rule as well, so negative 2x up the top. And here we have x right down here. So if we do, remember our integration by parts, so that means in will equals to x over 1 plus x squared half n between 0 and 1 minus the integral of this times this. So negative 2x over n times 1 plus x squared n plus 1 times x dx. And that's no space. Space. 1 sec. Yeah, all right. So if I substitute that in, that'll be 1 over 1. Well, no, I'm missing an n here. Oh, no, I'm not missing an n here. So I'll get 2 to the power of n minus, well, that's 0. So and then I'll plus the integral from 2x. Let's put a 2 to the front. And 1. Well, let me move the n outside as well. 1 plus x squared, n plus 1, x squared up top, dx. So where do we go from here? So we need to kind of form n plus 1, right? And we have n plus 1 down the top, so all we need to do is make the top 1, right? So how can we do that? And we kind of want to make another in. So a really good trick is to always look for plus or minus 1s. So if I plus 1 here, and I minus here again, that'll give me x squared plus 1 over 1 plus x squared to the power of n plus 1 and minus 1 over 1 plus x squared to the power of n plus 1. Right. And so that will just simplify down to 1 over 1 plus x squared n, and that will be 1 over 1 plus x squared n plus 1. Right. So that means if we put it back into our integral, it'll be 1 over 2 to the power of n plus 2 over n. Oh, and if we look at the integral across these two, this will just be in, right? In, and that would just be in plus 1, right? Because now the n here has become n plus 1. So we just go in minus in plus 1. Wait, through. Yes. Okay, so in equals to 1 over, wait, what am I doing? This should be up here, my bad. This should be up here. My bad. Yes, 2 to the power of n plus 2n in minus 2n in plus 1. And if we keep simplifying out, so 2n in plus 1 goes to 2n minus 1 in plus 1 over 2 to the power of n. That means in plus 1 equals to, if we divide everything by 2n, it'll be 1 over 2, well, n to the power of 2, n plus 1, plus 2n minus 1 over 2n in. There we go, got there in the end. I hope that was all right. Oh, don't worry, I'll show you a cleaner version after this. So you can take a picture of that. So. All good. Do I need to like go back and like explain anything? No? Good. Perhaps. Great. Yeah, here's a cleaner version of it. But yeah, for reduction formula, just remember when to use integration by parts and when not to. Great. Yeah, and then the last bit is just substituting trick. So because we can use some of the identities, such as 1 equals to cos squared theta plus sine squared theta. These will work really well for example, like these ones. I won't go in depth into each one because we're in a bit of time crunch. So yeah, but you can also use hyperbolic trick. For example, hyperbolic trick. If you're more comfortable with them, go for it. I personally use trick, but sometimes hyperbolic can be very helpful. Yeah, okay, let's have a look at this. I'll just have you look at it. Think about which one we're gonna use. And we'll go from there. Yeah, okay. So if we look at here, we try to spot any one of these in here. Wow, look at what we have. We have x squared minus 1. Which one does that look like? This one, right? And what does a equal? A equals to 1, right? So we can let x to be equal, well, since a is 1, that just be sec theta, right? And since d dx over d theta is equals to sec theta tan theta. Dx equals to sec theta tan theta d theta. And we just substitute everything back in. So that would be sec theta tan theta over, or d theta, over sec theta. And what's, well, 1 plus tan square theta is equal to sec square theta, right? That is tan square theta equals to sec square theta minus 1, right? And well, if we turn this into sec square theta, that means this entire thing will become tan theta, tan square theta. And if we apply the square root to it, that will give us tan theta instead. So that will equal to integral of d theta. That's equal to theta plus c. So I'll just put this into my Mobius, into my exam, and I realized I lost 5 marks because of it. Because don't forget to actually get the answer in terms of x, not in terms of theta. If you do, that's a shame, because you're just missing the tab in. So yeah, so that's all I need to do is I need to have cos, or inverse cos of 1 over x plus c, because that's just sec 1 over cos theta is x, right? So cos theta is 1 over x. So you can just go right here. Great. So here's the answers if you want to take a photo. Okay, great. Okay, so partial fractions. So we use partial fractions if the bottom can be fit. Oh, ignore the given that. So we use partial fractions if we see the bottom, and we see, oh wow, it's kind of nicely factorized, and the degree of the numerator is less than that of the denominator. If it's bigger, then just simplify it out and have a constant up the front, and then you can still do the same for the bits behind it. So how we do it is we let 3x squared minus 2x over x squared plus 2 times x plus 3. We let that to be equal to over x squared plus 2. So if it's x squared, we want the numerator to be ax plus b. So there's an x at the front. Well, it'll be like this. So it will always be 1 degree less than that of the denominator. So if it's x plus 3, that means the degree is 1, right? And what's 1 less than 1? 0. So, and what's degree 0? Just a number, right? So let's say c. Let's use capital letters. A, B, and C for x plus 3. So, and then you can just times these two over, get to here, and then you can get rid of the get rid of the denominators. So it'd be 3x squared minus 2x minus 11 equals to ax plus b times x plus 3 plus c times x squared plus 2. So if you expand it out, so ax squared plus 3ax plus bx plus 3b plus cx squared plus 2c. And if we tidy it up a tiny bit, so a plus b, x squared plus 3a plus b plus 3b plus 2c. Right. But so that's a bit annoying to solve, right? So what we can actually do is here, we can actually substitute numbers into this expression here, right? So if we substitute -3 in here, because this, we need to kind of you can kind of use a matrix to solve, but we don't like matrix. So if we substitute -3 in here, this will become 0, right? So that's neat, right? So 3 times -3 squared minus 2 times -3 minus 11 equals to c times -3 squared plus 2. And I don't have my calculator, so I'll just ruin it and let you know that c equals to 2. Yeah. Well, so that means this will be 2. And if we compare now coefficients between these ones, so that means a plus c is equals to 3. So if c is 2, a is 1. Surprise. So and if 3b plus 2c is equals to -11. So if we put in c is 2, we get 3b plus 4 equals to negative 11, or b is just negative 5. Right. So this is how you do partial fractions. So that means the integral of 3x squared minus 2x minus 11 over x squared plus 2 times x plus 3 dx will equal the integral of a is 1, b is negative 5, so it's x minus 5 over x squared plus 2 plus, well, c is 2 over x plus 3 dx. So this should hopefully look a bit more this way easier to solve, right? So I'm running out of space. That page. So from here, this is just a simple logarithmic. So this kind of is as well, but let's work with this one first. Oops. So this would be 2 ln, but don't forget the absolute value, x plus 3, plus half, well, because we need to add a half in for this to be for x to be the derivative of x squared plus 2. And then we have ln. You can add an absolute value, but it's kind of not necessary because x squared will always be positive, well, non-negative, and if I plus 2, that'll always be positive. So that, and then minus that one, it's a bit more special. You need to use the arctan or tan inverse. To be 5 over, it'll be the square root of this, so it'll be square root of 2, the inverse tan of x, or it'll be this over the square root of this. So it'll be x over the square root of 2 plus c. Good. I'll zoom out a bit. Okay, let's keep going. So that's the answers, but they didn't have the partial fractions. So yeah. Okay. So now that's done with our integration techniques. Now let's move on to ODEs. So types of ODEs. So we go over the first one, the separable one. That's the easiest one to solve. Well, usually easiest. Then first order exact, and then the last week we finish off the second order linear ODEs. Okay, so separable ODEs is easiest. So that means if it's in the form something like this, we can just simply move this to the other side, and then move the dx to the right, and then we can just integrate both sides. So for example, if you look at this one, I can just move the y's to the other side by dividing both sides by y squared. That's equal to 4x to the power 4. Move the dx to the right hand side equals to this. Integrate both sides. That's just I got space. Go here. Negative 1 over y equals to 4 over 5 x to the power 5. Don't forget your constant plus c. So that means y equals to negative 1 over 4 over 5 x to the power 5 plus c, where c is a constant. That's the simplest side of simplest version of ODEs, and yeah, good. Alright, great. So the next one we look at is where you can use substitution. If the form looks like this, we can substitute y equals to vx, where v is a function in terms of x, but don't forget to differentiate y to get something like this. So if that means y dash equals to x v dash plus v by product rule. So that means dy over dx equals to x dv over dx plus v. Right, so when can we actually use this? Because it's very hard, sometimes it's quite annoying to actually write out functions in terms of y over x. So all we should do is we need to show that this holds, and then that means we can use this ODE with substitution. Great, so best way to do this is with an example. So if we need to consider this ODE, we need to determine the general solution. And so yeah, so let's check if we can actually use this technique, right? So we need to require to prove that f of xy equals to f of lambda x lambda y, where lambda is just a constant. So if we substitute that in, so if we look at just this bit, this would be lambda x times lambda y plus lambda y all squared over lambda x all squared. So that would just equal to lambda squared xy plus lambda squared y squared over lambda squared x squared. And the lambda squares all cancel out, so that's xy plus y squared over x squared. And that's equal to f of xy. So that means we can use this substitution, and then we can just try that. So that means y equals to vx, dy over dx equals to x dv over dx plus v. And then we substitute that in, so x dv over dx plus v equals to, well, since y equals to vx, well, actually I'll substitute into the y. So x times vx plus vx all squared divided by x squared. So if you can see, the x squares kind of cancel out, so that means x dv over dx plus v equals to v plus v squared. We minus v for both sides, so x dv over dx equals to v squared. Now we have a nice and easy separable differential equation. Well, divide both sides by x, that's clearer. So now we have a separable differential equation. So that means dv over v squared equals to dx over x. Take the integral on both sides, so negative 1 over v equals to ln absolute value of x plus c. So, but we can't just leave it like that, right? Don't represent it in terms of v. Always go back to representing in terms of y, because they asked us to represent in terms of y. So 1 over v, since v equals to y over x, 1 over v is just x over y. So that means negative x over y equals to ln absolute value of x plus c. And if we just do a quick algebra, just negative x over ln absolute value of x plus c. And that will be our general solution. All right, good. Let's push on. Yeah. So here's the full solution. Yeah. So the substitution will ultimately get you back to a separable, hopefully get you back to a separable DEQ, and then will be way easier. All right, great. So our first order linear equation will be in the form of this, and then all we can do, this should be a cubed. So yeah. So if we want to do this, here are 4 steps we actually can follow. So we need to, from here, we can't really, well, we can, but like it's quite hard. So we need to write in terms of this. So if we divide everything by 2, it'll be dy over dx plus 2x cubed y equals to 3 over 2x cubed. So that means f of x. So that means this bit will just be f of x, and this bit will just be g of x. And then from here, we can define what we call an integrating factor, and it will be the e to the integral of the e to the power of the integral of f of x. So, and we don't need to care about the constant if we integrate it, because that will just kind of cancel out after we do all our work. So if we look at that, that was e to the integral of 2x cubed dx, right? So that means e to the power of half to the power of x to the power of 4, and we ignore the constant, so don't write it plus c. And so we can multiply the entire ODE by this. So on the left-hand side and the right-hand side. And eventually, this will look like a product rule, right? Because this will be the product rule. And that means we can just finally get to this right here. And that means if we substitute everything in, so d of dx, h of x will be, so this is our h of x. So that means e to the power of half x to the power of 4 times y equals to gx, that is 3 over 2, x to the power of 3, e to the power of half x to the power of 4. And then that should simplify out nicely to, well, if we integrate both sides with respect to x, this would just be a simple reverse chain rule. So e to the power of half x to the power of 4 y equals to 3 over 2, 3 over 4 instead, because like there's a half here. E to the power of half x to the power of 4. But now this time here, we will need the constant, so plus c. So y will equal to 3 over 4 plus c times e to the half, negative half this time, negative half x to the power of 4. And this will be our general solution. Oh, it's right here. Oh, there it is. Yeah, so it's a bit cramped. But yeah, so this is how you solve a general one, and yeah. So let's do another example, this time type it harder. So this is an IVP, so that means they give you a value. And usually for general solution, we leave in the C, right? So for an IVP, you actually need to solve it to actually find a value for C. And then, yeah, where is it? Next page. Oh, there. So if I have that, I'll just keep it up there. So that means this will be include a negative as well, because if we look up here, this should be a plus, right? So it's not minus. That means this entire thing will be f of x, and this is g of x, right? So that means integrating factor. Well, you can use that, or you can use h of x. Equals to e to power of the integral of negative x over 1 minus x squared dx, and that's equal to e to the power of half ln the absolute value of 1 minus x squared. And that, because like e to the power of ln something just equals something, so that was just equal to the square root of 1 minus x squared. Good. So that means d over dx, the square root of 1 minus x squared, because this will need times the integrating factor times by y equals to the integrating factor times what's on the right hand side, so 2 over 1 minus x squared. So that's equal to 2 over square root of 1 minus x squared. And I hope you recognize something like this. This would just be the arc sine or sine inverse. So that means square root of 1 minus x squared times y will equals to 2 times sine inverse of x. But this time we need to add the plus c. So y will equals to 2 sine inverse of x over 1 minus x squared plus c over square root of 1 minus x squared. And if we substitute in the condition, y when x equals 0, y equals to 1, so that's 1. That's 0, sine inverse of 0, that's 0. So that's gone. So 1 was 1 minus 0, that's 1. So that's 1. So it means c equals to 1. And you can just plot that value. And so that's your solution to the IVP. So here. Great. Okay, I'll keep going because bit of time crunch. So yeah, so next we have some exact ODEs. So exact ODEs are in the form of this, but this is a very important condition that it must have. Sorry. Without this condition, it is not an exact ODE. So always be sure to check it before you start solving it. And if this is satisfied, that means there is a function h of xy equals to a constant where the derivative of h with respect to x equals to this, and with respect to y equals to this. So a good way to remember this is to check. You take the partial derivative with respect to y, and then that means the h will have a partial derivative with respect to x equals to this. And all that's the reason why is because, if you remember up the top, the partial derivative of x and y, it doesn't matter which order it goes in. So that's kind of why this function h exists. Yeah, great. Okay, so it's kind of a bit annoying to describe it. So let's just work through an example. I need more space. Okay, here we go. Okay, so if we look at this, let's first check that it is actually an exact solution. So we need to move so this will be our f, and this would be our g. So if we look at the partial derivative with respect to y, that's equal to sec squared y. That's just it. And we look at that with respect to x, that will be constant, right? So, and that's gone, and that's 1. So that will equal to sec squared y. So that's equal to the partial derivative with respect to y. So that means it is exact. Good. Okay. So now we can. So that means there's an h, which if I take the partial derivative with respect to x will equal to f, right? So that's tan y minus 2x. So let's take the integral with respect to x. Right, so the left hand side will just be h, and then the right hand side will just be tan x times tan 2y minus x squared plus, firstly we need a constant, but there'll also be, the constant will now also include a function in terms of only y, right? Because that would just be, we would treat that as a constant if we integrate, we take the partial derivative with respect to x, so that's equal to g of y. So if we now take the partial derivative of h with respect to y, that would give us 2x sec squared 2y minus, wait, 10, where did 2y come from? That's y. Okay, that, and then that will just be gone, and then that will also be gone, plus the derivative of g with respect to y, and that should equal to g, right? Which is x sec squared y minus 2y. So that means if we compare terms, that means the derivative of g with small g will equal to negative 2y. That means g of y, which is equal to negative y squared plus c. All right, so that means h x y c2. So we're equal to x tan y minus x squared plus c1 minus y squared plus c2, and that's equal constant. That means the solution. We can kind of ignore the constants because that will equal constant, so that will all cancel out. That can just move to the other side. So that means the solution, final solution will be x tan y minus x squared minus y squared equals a constant. Good. Okay, great. Okay, no questions. Okay, so here's the full solutions that will be uploaded to the website, I think, afterwards. Yeah, okay. So let's move on to the last bit on ODEs. So a second order homogeneous, depends how you say it. Homogeneous ODE just means that the right hand side is 0, and the height or the function y we like take into the derivative like twice. And yeah, so we need to always see that this will always be a solution, or something in the form of this will always be a solution, and we can always find a characteristic equation. So something like this. So basically, to get to this, all you do is replace this, so dy over dx with a lambda. So if it's taken into the second derivative, that will just equals to lambda squared, right? So, and that's how you get from here to here. So if you solve this, if you solve this, that means give you 2 real roots. So that means you can substitute into this lambda right here. And if they're different, it'll give you something like this. But if they are the same, so for example, you get a double root. So for the second one, you need times by x. And then yeah, so if you have somehow a complex root, then you need to represent it into a alpha plus beta I, and then you can substitute into this form. Yeah, if you want a photo, now's the time. All right, great, let's move on. Yeah, great. So yeah, so let's do this as an example. So to get to our characteristic equation, so we need to replace the dy over dx with a lambda, well, since it's d squared y over dx squared, that's lambda squared plus 4 lambda plus 4. And since y will just be 1, so that's equals 0. We solve that equals to, so that means lambda equals to -2. So we have double root, right? So that means y will equal to a times e to the power of -2x plus b, but this times times by x, e to the power of -2x as well. So if we then substitute our condition into here, so that means this will become 0, this will become 0, so that means a is 0, because this will become 1. So 0 equals to a times 1 plus 0, so a equals 0. Great, and that means y, which is equal to b x e to the power of -2x, and b, well, b is some random constant that we pick. Good. Okay, sorry. Okay, so we look at a homogeneous case. Now we look at a non-homogeneous case. So the only difference is that instead of 0, now the right-hand side is replaced by f of x. So that could be like x plus 1 e to the power of ax, or whatever we pick. Okay, so to do this, we need to let y equals to the homogeneous part plus something we call a particular solution, where we can have multiple guesses to what it could be. So for example, if the f(x) is a polynomial, then we'll guess that yp will also be something like a polynomial. But if it's something, for example, an exponential, it'll be like a similar sorry, it'll be like a literal similar version of it. But yeah, so if it's like cos x, you need to cos x or sin x. Don't forget to have cos x plus sin x times by different factors in front of it. And yeah, so it's same thing for these ones. Yeah, so if it's a combination of them, you just put in a combination of different ones. So yeah. Photo? No one? Okay, skip. Okay, so best way to look at this is through an example. So, one sec. Wait, it is. Okay, so the first thing we do is we need to consider the homogeneous part and the particular solution. To find the homogeneous part, we just treat it as like a normal one where this is 0 over here, and to solve it, we just let y double dash to be lambda squared. That's 5 lambda and plus 6 equals 0. That means lambda equals to 3 and lambda equals to 2. Right. So that means our homogeneous part equals to a to the power of e 3x plus b e to the power of -2x. And the particular bit, since the right hand side looks something like this, but we've seen that just 2x. But we see that this part is already here, right? So that means now the particular bit, we can't just let it to be, for example, ce2x. That doesn't work because we already have it here. So we need to similar to how we did it up here. If this has already occurred before, we need to times the particular solution by x. So it'll be x e to the power of e to the power of 2x. And then if we substitute back in, so y, if we differentiate one time, it will be, yeah, I hope people can do it by itself. I'm just gonna skip to the answer of the derivative because we're running a bit behind. e to the power of 2x plus 2x e to the power of 2x. And if we take the second derivative, it will be c times 4e to the power of 2x plus 4x e to the power of 2x. So yeah, so if we substitute it all back in, so that means c times 4e to the power of 2x plus 4x e to the power of 2x minus 5c e to the power of 2x plus 2x e to 2x plus 6c x e to 2x equals to 10 e to the power of 2x. Right, so that means we can cancel out everything out. So 4c plus 4cx minus 5c minus 10cx plus 6cx. So this will cancel out. Then that will equal 0, equal to 10. So that means negative c equals to 10. So that means c equals to negative 10. Oh, oops. That page. Where were we? Ah, here we are. Okay, so that means yp will equal to negative 10x to the power of e to x. So y will equal to yh plus yp, right? So that means equals to a to the power of e 3x plus b e 2x minus 10x e to the power of 2x. And then since it's an IVP, you can just substitute the values in, and then you can take the derivative and then substitute it again. But in the interest of time, let's not do that. And spoilers, here's the answer. Yeah. Great. That's all done for me. Yeah, it's now Angela. Go for Taylor series.
Okay. Alright. First things first, since I noticed there's a lot of people who showed up after the beginning, I'm just gonna scroll all the way back up because everyone needs to do the attendance. Yeah. Right. Can everyone who didn't do the attendance please do that? We need money.
I think you need to say that.
Okay. Yeah. Okay, everyone scanned it? Right. Oh gosh. Okay. I'm Angela. I'll be taking over this part of the seminar. So let's start with Taylor series. Okay. So sequences. A sequence is a function with the natural numbers as its domain and real numbers as its codomain. And they have this notation. They're usually defined by a rule which tells us how to find each term. They can be defined like this or recursively like this. Right. Some sequence is called convergent if its terms approach some finite number as n goes to infinity. And if it's not convergent, then we just call it divergent. Now, if this sequence is defined by some rule, and that rule can be written as a function as we usually know it, then if the limit of the function exists, then the limit of the sequence exists and is equal to the limit of that function. Right? Right, question 1. So determine whether this sequence, defined like this, where a is greater or equal to b and they're both positive, converges or diverges as n goes to infinity. And if it converges, find its limit. So, for this, I'm actually going to say that I'm guessing that this is just going to converge because of how there's just one n power here. And maybe there's some kind of cancellation with this. So I'm going to try to prove that it converges and find its limit. Alright. So I'm going to rewrite it. Okay, and this will let me write the a by itself times with this thing. Okay, and now this is gonna be, here there's two cases. So either b equals a, in which case this b over a is going to be 1, and then this thing is going to be 1. And so what's going to happen is that this is 2. So this whole thing, because that's going to approach 0, this whole thing is going to approach 1. And in the other case, if b is less than a, this whole thing is going to approach 0. So this thing is going to approach 1 over 1 to the power of 0, and that's going to be 1. So in either case, this thing is going to approach a times 1, which is a. Right. So this is its limit as n goes to infinity. Any questions? Okay, nice. This is basically the same idea. Okay. Sequences. Now, sequences are a type of function with the same domain. So we can add, subtract, multiply, divide them to produce a new sequence. For example, like this. And if two sequences are convergent, then the same applies to their sum, difference, and product. So, for example, the product. For dividing two sequences, it's a bit different because there's this case. Yeah. Now this is a table of the relative order of growth of different sequences or different terms in the sequence. This is good to know as a tool for intuitively deciding whether you think it will converge or diverge. Okay. Right. The pinching theorem. So this pinching theorem from the ordinary functions can also be applied to this. It's basically the same idea. If one sequence is sandwiched between two others, and the ones that it's sandwiched between both converge to the limit L, then Bn is also going to converge to L. Okay. And this is another test for convergence. First, we have a definition. Monotonic means it's either all increasing, or non-decreasing, or decreasing, or non-increasing for all n. And another definition is that a sequence is bounded above if there exists some number m such that every term in that sequence is at most m. And then same thing for bounded below. If there exists some number m such that every term in the sequence is at least some m. Okay. And if a sequence is bounded and monotonic, then it will converge to some real number L. This is the other test for convergence. Right, here's an example. So show that this sequence converges. Okay, so what I'm going to do is I'm going to use this theorem, this test, to show that it converges. So I need to prove that it's bounded, and this one I think is going to be increasing. This is what I'll set out to prove. So, first, boundedness. Here, I claim that this is bounded between these. And then I'm going to prove this. How we get 1 is from here. How we get 2, that's kind of a guess that seems like it might work. And now I'm going to do this by induction. So A1, that's obviously in here. So now we need to suppose that some kth term is between these bounds. And then that means that right. Then we do this. And so we have root 2 and root 3 here. And we know that root 2, that's going to be greater than 1, and root 3 is less than 2. So this means that, oh, that should be okay. The k plus 1th term is going to be bounded between this. And so we've proven boundedness by induction. Now to prove it, that's increasing. So base case, A1 equals 1, and A2, or we can get it from the formula, it's going to be that. Clearly this is increasing. So that's our base case done. And now suppose there's some AK and it's greater than its previous term. Okay. Now we want to show that this AK plus 1 is greater than AK. Now first, I'll just use the definition of it. And now, to prove that this is greater than the previous term, I want to use this inductive hypothesis. So since AK is greater than AK minus 1, I can do this. And this is fine because the square root function is increasing. And then what I see now is that this term, the square root 1 plus AK minus 1, this is exactly what describes the term AK. And so AK plus 1 is greater than AK. Okay. So we know now that's increasing and it's bounded. So by the previous theorem, because it's increasing and bounded, it's going to converge to some limit. Okay, any questions? Right. Here's the solution nicely typed up. Okay. Suprema and infima. So the supremum of a sequence is its least upper bound. This means that it's an upper bound and it's smaller than all other upper bounds for the sequence. Similarly, the infimum is just that, but it's the greatest lower bound. So it's a lower bound and it's greater than all other lower bounds. Okay. Find the supremum and infimum of the following set. So let's see. Supremum. Well, for this, we want to find its lowest upper bound. Now, if I actually rewrite this a bit, we can see that as n gets bigger and bigger, this just keeps getting bigger, whereas this goes to 1. So that just means that this just keeps increasing. And so if it keeps increasing, there is no upper bound for it. So it doesn't exist. Right, so what about the infimum? Well, from the logic of before, this increases, whereas this decreases. Whenever this increases, it's going to increase by 1. But this is going to decrease by less than 1. And so this is an increasing sequence. And so, because it's an increasing sequence, then the greatest lower bound is just going to be whatever the first number in that sequence is. Just going to be okay. Any questions? Right. Okay. This is the same thing. Infinite series. So a partial sum represents the sum of all the terms in the sequence up to a certain term. Now, if this partial sum approaches some limit, then we say the infinite series is summable and converges to L. If it doesn't approach some finite number, then it diverges. Now, since these summable series are going to be equal to some real number, given that they're summable, then we can manipulate the summations in these kinds of ways. So if this exists, and this exists, and this exists, then this is fine. If this exists, then this is fine. Alright. And for infinite series, the first finite number of terms are irrelevant to whether it converges or not, because the first finite number of terms aren't going to make it blow up to infinity or do other divergent stuff. And this is the way that this idea is written in symbols. Okay. The kth term test. If the sequence, so if the actual terms in the sequence don't approach 0 as k approaches infinity, then the series of that sequence has to diverge. And because of the same kind of logic, we know that if the series converges, well, then this has to have a limit of 0, because otherwise the series would diverge. Okay. Comparison test. Suppose that these are all non-negative terms and that AK is less than or equal to BK. Right, so if the series of BK converges, then the series of AK will also converge. And if the series of AK diverges, then the series of BK will also diverge. And the final thing, a P series will converge if P greater than 1 and will diverge otherwise. Right. Does anyone have questions about any of these comparison tests? Okay, all good? Right. And the integral test. So replacing the rule for the sequence with function of x. If the function is continuous and positive and decreasing on this interval, then the integral test can be used. So if this integral converges, then the series does. If it diverges, then the series diverges. And finally, the ratio test. So suppose that this series is an infinite series with positive terms, and that the limit of the k plus 1th term and the kth term divided like this is equal to r. If r is less than 1, then this converges. If r is greater than 1, it diverges. If r equals 1, then we can't use this to say anything about convergence or divergence. Okay. Here's an example. So it's to determine whether this series converges or diverges. For this, because there's this factorial term, I'm going to choose to use the ratio test, because ratio test is good for dealing with factorials. Okay. Now we can get a bunch of cancellations here. So this 3 to the power of k is going to cancel out with most of these powers. And this k plus 7 factorial and the k plus 6 factorial, well, all of those terms are going to cancel out except for the k plus 7. And what we're left with is 3 times k plus 7 Okay. Wait, Conrad, how do you add a new page?
Top right, see the two papers. At top right. Yeah.
Okay, thanks.
3 dots. Add page. Oh no. Wait. 3 dots like next to 100. Next to, yeah. Add page.
Okay, thanks.
And you click the top right again, like get rid of that.
Okay. Okay. Now, with this, so this k plus 7, this is kind of annoying because it's just a term on its own. So I want to try to find a way to simplify this thing. So what I'm going to do is I'm just going to use the fact that that's going to be bigger than. Right. Now this is more simplified, and I just have to hope that this will say that it's bigger than 1, because then that's how we're going to get a result from the ratio test. Now, if I rewrite this a bit, this kind of expression should look vaguely similar to the expression for the limit of e. So I'm going to rewrite it to match that expression. Okay. Now here what we notice is as k goes to infinity, then the 3 is just a 3. This term, that's just the same as the limit for e. It doesn't matter that there's a k plus 3 instead of a k, because when it gets really large, then it's roughly the same thing. Oh wait, there's a squared there. Oops. Okay, and this thing, well, k plus 4 over k plus 3, that approaches 1. And 1 squared is just 1. So it approaches this. Okay. That's equal to 3 over e. And e is 2 point something, so 3 over e is going to be greater than 1. So if we look back at the limit of the ratio is going to be greater than this, and that's greater than 1. So we can deduce that the limit of this is going to be greater than 1. So by the ratio test, this is going to diverge. Oh, that's the wrong button. Okay. Is everyone happy with that? Okay. And this is the same thing. Okay. On to the Leibniz test. So an alternating series is one whose terms have alternating signs between positive and negative. And they're written like this. Now, an alternating series will converge if the positive versions of its terms, that means that these terms, not the part that's not the negative 1 part, satisfy the following. So all of those terms are not negative, and those terms are decreasing or non-increasing, and the limit of those terms approaches 0. So if it satisfies these conditions, then the alternating series will converge. Okay. A series is absolutely convergent if the absolute value of all its terms summed together in a series is convergent. Now, if a series is absolutely convergent, then it's going to be convergent. If the series converges, but this doesn't converge, then it's conditionally convergent. Okay. Here's an example of a type of convergence. So determine whether this series absolutely or conditionally converges or diverges with reasons. Okay. So first, I'll find out if it absolutely converges. So does okay. Now for this, we can use the integral test. Oh no, that's not meant to be a 2. And now this is just a reverse chain rule. And we can see when we put the infinity in there, then that's going to diverge to infinity, and this is going to diverge to infinity. And so this definitely doesn't converge. So it does not absolutely converge. Okay, I'll do the working here then. Right. Okay. As for whether it conditionally converges, well, we can use the Leibniz test. So, yep, it is true that apart from this, all the terms are going to be positive. And then we can check the other conditions, which is that as n goes to infinity, this thing is going to go to infinity. So the limit of this whole thing is going to be 0. And now the only thing we need to check is that it's going to be non-increasing. So as n increases, this is going to increase. ln n is increasing, so this is also going to increase. And if the denominator increases, then the value of the whole thing must decrease. So yes, as n increases, this decreases, or the size of it decreases. We ignore this. Okay. Is everyone fine with that? Okay. Yep. So from the Leibniz test, it's going to conditionally converge. Yeah. This is the same thing. Okay. Taylor series. So these are infinite sums used to approximate functions near a certain value. And this is the formula that defines it. Now the Maclaurin series is just the Taylor series, but it's the Taylor series about a equals 0. Okay. Taylor's theorem says that if we have a Taylor polynomial for the function, then the function is equal to that plus some remainder term. Now this remainder term has two forms. The Lagrange form here is given by this. This can be remembered as being really similar to the n+1th term, but here we have a c instead, where c is some value between a and x. Okay. And if this limit of the remainder term approaches 0, then the approximation gets better and better for large n. These are some examples of Taylor series. Okay. The Taylor series is an example of a power series, which is a sum of this form, where ak is a sequence of coefficient, and then this is just x minus a to the power of k. Okay. Now convergence or divergence of these series depends on what x value we put in it. So if a power series converges for all points in some interval of x, like this, then R is going to be the radius of convergence, and this interval is called the interval of convergence. So the ratio test can be useful for finding this radius of convergence. If the limit of these two terms equals R, here notice that it's swapped around. The lower term is on the numerator rather than the high term. Then if this limit equals R, then R is the radius of convergence. And this is basically just stating what it means to be the radius of convergence. Also, the root test can be used, which is a good thing to know. And for 1231 students, you have to determine whether at the endpoints it will converge or not. So for this, you just put in the value at the endpoints and then use previous methods to determine if it will converge. Wait, I need water. Okay, here's an example. Find the open interval of convergence for this power series. So this is one where there's a lot of Kth powers. So what I'm going to use is the Kth root test. So the Kth root test is basically the same as the ratio test. Now what I'm going to do is I'm going to apply this Kth root test to the absolute value of this instead. Because if it's absolutely convergent, then it's going to be convergent. And I don't want to deal with cases where x is negative. Right. So Kth root of that expression is going to be ln k times absolute value of x, because we're dealing with the absolute series here. And for any value of x, as k approaches infinity, then ln k over k is going to approach 0. So that's going to be 0. So what this means is that because of the Kth root test, since the limit of the Kth root of this is less than 1, then this is going to converge for every single value of x. Okay. Any questions? Okay. Power series. Within the intervals of convergence, you can add, multiply, differentiate, integrate power series. As long as you're working in these intervals. Okay. Question. So write down the Taylor series for fx equals sine x squared about x equals 0 and state its radius of convergence. Here, what I'm going to do is I'm going to use the fact that sine x equals I hope I'm remembering this correctly. It's this. And from that, we can determine that this is going to be the Taylor series for sine x squared. This is just what happens when we substitute the x squared into this function. And now we have to think about its radius of convergence. So because this converges for all x, this is just something we know about the Maclaurin series for sine. And so that means whatever input we have in here, this is going to converge. So for any input x squared that we're putting in here, then this will converge because of that. Right. Any questions? Okay. Applications of integration. Right. The average value of a function is going to be the integral of it over how large the interval is. And the mean value theorem for integrals is that if we have a continuous function on some interval, then there's some c in the open interval such that this is true. If we want to think about it intuitively, suppose that's ft, a and b, then there's some value c such that the area of this is going to be the area of this rectangle is going to be equal to the integral of this function. What the? Okay. And we can also rewrite this to get the usual mean value theorem. See, that's true. Okay. Arc length of a curve. If a curve is expressed in the following parametric form, then the length of the curve can be calculated by this. Okay. And then if the curve is expressed as a function of x, then the formula becomes this instead. This can be easily proven using the parametrization where x equals t and then y equals that function of t. What? Okay. Right, here's a question. So let hx equals cos x in this interval, and define L to be the arc length of the graph of h in that interval, and define A to be the area bounded by the graph of h and the x-axis between these values, so in the interval as well. Prove that the length equals that area. Okay. So I'm going to use this formula for the arc length. And that's going to be this. Okay. Now I'm actually not going to integrate this because if we think about how we would find the area, well, the area bounded by the graph and the x-axis between the x's a and x's b, that's just going to be the absolute value of this hx. So the absolute value of cos x integrated from a to b. And then you can see these are the same. So we get that the arc length is the same as that area. Okay. And this is the same thing. Here we also have the arc length of a curve when it's expressed in polar coordinates. This you can also get from parametrizing the equation. And this is the surface area formula. This one, there's a good proof of this in the course notes. And these two are similarly to before. You get these two from parametrizing the equations. So this is for parametric equation. This is for y as a function of x. And this is for polar equations. Okay. Here's this last question. So a cone with a base radius r and a perpendicular height h is formed by rotating this line segment about the x-axis. Then use calculus to show that the surface area S of the curved surface of the cone is given by this equation. So these were the formulas for the surface area about when we rotate a curve about the axis. I'll point out that what these formulas actually give us is the surface area of this part and on the back as well, but I can't color in the back. What it doesn't give is the surface area of this flat part of the cone. But here, actually the question just wants us to find the surface area of the curved surface of the cone, so this part. So we can just directly use the formula. So what we get is A equals integral from 0 to h 2 pi times y. And then what we get is now we want to put the derivative squared here, and the derivative dy over dx is just going to be r over h, and it should be a dx at the end there. Can't really fit it in. And here, well, we're integrating with respect to x, and since most of these things are actually constants, I'll just pull them out of the integral. Okay. And so integrating, we get this. Then we get this. Now this will cancel out. These 2's will cancel out. And so we get pi r square root of that times h. If we simplify this a bit more, we get this. And we can see that this is the same equation that we needed to prove. So we're done. Okay, good with this? Okay. Is this, okay. Yeah. All right, that's basically the end of the seminar. Just a few last things. So seminar recordings. This is recorded on YouTube. It will be on our YouTube channel. Just search this. And you can also find our seminars from previous years here. There are a non-zero number of changes to the seminars every year. And what? If you can't find these in the videos section of the channel, check the live section.
Why is this
Yep.
scripted?
Last thing, there's this and the feedback form.
Thanks for coming. Thanks for coming to the stream.